Okay, welcome. It is nice to see everybody here. Thank you for making the trip. And it's sort of somewhat short notice, but I really do want to thank you for being here. I hope we have a good discussion today. Just came back from the Strata conference where there were a lot of people talking about big data and analytics and things I've been doing for a long time, basically, with Python. And there wasn't enough Python there, right? So that's essentially my frustration. And one of the things we're trying to figure out why and figure out how to fix. And so I'm glad everybody's here. And want to also give a shout out to the folks that Peter mentioned. Julie Steele was very helpful when the idea for this conference was hatched. She's very, very helpful getting us the facilities, getting us the location. Ed Dunville was on some calls as well. He was the organizer of the Strata conference. Really helped us out to make this possible. And then I want to give a shout out to Peter Wang. He did a lot of work making this happen. If we can give a round of applause to Peter, it'd be great. Thanks, Peter. He's a force of nature. If you get a chance to interact with him, it's a real treat. He's got but somebody said, you know, usually when you're listening to somebody just talk all the time, you get really bored. You don't get bored talking to Peter. I mean, you can just listen to him all day long, and he has something interesting to say. So, and most of that is relevant to Python, so it's pretty exciting. I'm excited to be working with him at Continuum. So, like I said, I just got back from the Strata conference, and talk about it a little bit. Some of you might have been there. Let's raise a hand. Who was at the Strata conference? Okay, that's great. I mean, the hope was we would be able to get some folks who were at the Strata conference to come and work together and talk about Python's use in similar areas. So at the Strata conference, you know, it's Hadoop all the time, Hadoop everywhere, and you're just drowned in Hadoop, and then R on occasion on the back of Hadoop everywhere. And Python, you don't really know where it's being used. Of course, if you go talk to people, you realize it's everywhere. People are using Python, they're using the tools to do things, but then it's just not, doesn't really have a big voice, big name. So that was, you know, why is that? Hopefully we'll talk a little bit about that during this conference. There were some interesting talks. I spent a lot of time in our booth actually talking to people coming by and actually just kind of receiving people who use Python and who wanted to come by and talk about how, you know, they were using it and maybe they could improve it. But I do remember Doug Cutting's talk, and he had a quote that said, Hadoop is the kernel of the new distributed OS, that sort of caught my attention. It's the first time I'd heard somebody in a talk say something that I've been thinking about for a while, that yeah, in fact, when you talk about an enormous number of machines, there is this need for an operating system or some way to communicate an application to communicate with all of those machines but seamlessly. So you're not worried about all the details of configuring that system. And in that sense, Hadoop has sort of emerged as this big player in that kernel. But from my perspective, that's not the kernel I want to be using. That's not the kernel I want to be having to interact with. And I'll explain why in a minute. And Mike Olson, the CEO of Cloudera, gave a nice talk on guns, drugs, and oil, just basically showing use cases of big data. You know, big data has a bit of hype behind it, for sure. But at the core is this idea that we've got commodity hardware at your fingertips, the ability to do analysis on a lot of data. And there are a lot of big problems where people need a lot of data in order to make decisions that improve all of our lives. So it's an exciting time to be associated with some of these problems. One of the interesting talks I saw or heard about, actually, was Google, of course, is always on the cusp of big data. In some sense, it's because of their commoditization of the data center that we have the notion of big data and the kind of ability to use commodity hardware in a unified fashion. But they've been pioneering using search terms to track things. Of course, you've all heard about using search terms to find outbreaks of disease, people searching for medicines. Well, there's another talk on the market state, people searching for terms related to, well, you know, looking for unemployment benefits or something, or, you know, house prices, you know, people searching for houses. You can actually, there's some research that shows you can predict the state of the market or trends in the market based on Google search terms. Interesting aspect, interesting application of big data. And then another talk that I liked because I saw it relevant to a lot of the people I've associated with in my life is the SciDB talk. But it also opened it helped me see that there were some real things we need to focus on in the Python community to ensure that Python stays relevant as the march to big data emerges. So if those who aren't familiar with just how many areas of big data, these are ones that came out of a blog. Big data is the answer, what was the question? It's a really nice blog, actually. And he lists a bunch of use cases, which is exactly the right way to think when you're thinking about big data. You don't want to think about big data in the abstract. until you've actually tackled specific use cases. Like, this is what I'm actually trying to solve, and it's got a lot of data, and here's the problem I'm trying to solve. And there's a bunch of them. This is one he listed: retail, telecommunications, utilities, financial services. But he didn't even cover the areas that I would say, if you talked about big data, what would I come up with? This big science, the data collection from CERN, astronomy, bioinformatics, weather and remote sensing. I was at the American Meteorological Society convention where they have sensors all over the planet, not just in the air looking down at us through satellite, but they've got devices measuring wind speeds and barometers and pressure sensors all over the place. And all of those data they've been trying to figure out for a long time to predict weather. Right? They sort of started big data. They're heavy Python users, right? And their use of it doesn't really show up in a lot of radars. So weather, remote sensing, research experiments in general. IBM has a sensor of the planet notion. Spent a lot of time in New York last year, for better or for worse. A lot of time in Manhattan. Racked up JetBlue miles so that my wife can actually come visit me now. She's going to fly out for free on JetBlue to San Francisco because of all those miles. But every time I walked into the New York airport, I saw IBM's posters that said, make the world a smarter planet, right? By essentially putting sensors everywhere and taking those data and then making predictions, trying to do traffic flow, trying to detect disease, trying to detect better food manufacturing. And then, of course, you've got oil exploration and industrial processes. These are projects that I've personally been involved with while working for NThought. And actually, I wanted to make sure and give a shout out to NThought. I think Peter mentioned it, but they were very gracious to provide the EPD trials for us so that we could get it all Python installed in everybody's computer very quickly. So I wanted to make sure and thank them. And while working for NThought, I had a lot of chance to look at a lot of companies, big data problems. They don't advertise themselves as big data problems, but they are in fact using a lot of data to try to answer important questions. So in particular, some of those places where Python is being used for big data, oil exploration. A lot of companies, there's a diagram on there showing how seismic information is captured. Many of you probably aren't familiar, but it's a pretty simple process. You have an air cannon, you explode sound waves down into the ocean. It bounces off layers in the ocean, under the subsurface of the ocean, and you take a huge train of sensors in the back behind that air cannon and just record the sound coming back from the different surfaces. It's a pretty raw data set, and from that data set, you're trying to infer what are the layers under the ocean. Based on the speed of sound, when the air cannon shot, when you're measuring the sound, so you kind of know if you get it this time, it must have bounced from this layer, and what was the signal amplitude. You can infer, okay, how much was transmitted. You have to basically unravel all this data into this picture of the ocean floor to try to find salt domes, shale layers, places between sand and shale where oil will accumulate. You're looking for oil. Big deal. Using whatever tool they can find, right, to do this. It doesn't matter. There are no language bigots when you're trying to solve a problem, right? You just want to use your tools to solve your problem. It doesn't matter what it is. But Python's in use. There's a lot of people using Python, and sort of why is that is an important question, an important question we should continue to consider. On Wall Street, there's a lot of large banks using Python. There's a lot of hedge funds using Python to understand their tick data, understand pricing data, and make a lot of decisions about it. I actually have somebody here that I know I've had a chance to work with on Wall Street solving a counterparty exposure problem. Everybody's aware of the big problems that occurred in 2008 when the market crashed. Actually, some of the banks did pretty well because they had some semblance of a notion of what their positions were when all the positions started to unravel and people started going bankrupt. And people knew how they would be impacted by people going bankrupt. Not everybody did. It's Lehman Brothers, they asked, people would try to find out, well, what's going to happen if these guys go bankrupt? And actually, they didn't really know. It took them a while to figure that out. And, day before they were out of money is when they figured it out. Exposure to companies going bankrupt when you've got all these deals and complicated transactions between those, figuring that out, and you've got transactions happening, thousands of transactions happening a day, hundreds of thousands of transactions happening a day. What does that do to your net position, and how is it changing? Important real data problem, big data problem. Then, of course, the genome, bioinformatics, huge amounts of data being generated there. And Python's in use. So how does Python swallow the elephant of Hadoop? That's, it actually is in many ways. I guess this is my reaction to all the hype that I saw the past couple of days. And I don't want to take anything away from Hadoop. Hadoop's a great project, and it does a lot of things really, really well, and it's paved the way, and it's being used in production. It's really exciting to see companies like Microsoft and Oracle kind of jump on the open source bandwagon and use tools that are available for everybody and get them out. So that's, the important thing is solving people's problems. But I do have a couple of questions. I heard that Hadoop is the distributed OS, and it's the de facto standard. Okay, why is that? Why is that? Why is R used so often in data analysis? Right? We all know that Python's a better language, so why is R used so often? Right? And this is a quote I heard from a very large company. They came over and said, well, we actually use Python all the time, Python and NumPy all the time. And they said, I use Python and NumPy to do all my data prototyping, my data analysis prototyping, and then I deploy to a Java Hadoop production system. Right? And I mean, that's frustrating to me. It's frustrating me for a couple of reasons. Why? Why should I care? Right? Well, there's a company called LexisNexis that they've actually been making a lot of money selling data analysis for lawyers, like legal studies and searching patents and searching all kinds of, they have teams of lawyers looking at rulings and trying to pull out relevant pieces of that in order to provide a database to other lawyers so they can search them. And they've been making a lot of money doing that. And they spun out a company called HPCC, High Performance Computing, and a bunch of people there wrote a data analysis platform, a distributed data platform. So you could use commodity hardware, put your data out there everywhere, and then have a relatively straightforward language to query it and to do analysis on it. They were at Strata and Force as well, and their engineers were basically, they turned to their CTO and said, if we don't do something, 5 years from now, we're all going to have to write in Hadoop. If my boss comes to me, I've got this tool that works, it's amazing, it's wonderful, but my boss is going to come to me and say, hey, how come this isn't Hadoop? Right? And they're going to be frustrated, like what happened? So in fact, they took some drastic measures. They released HPCC. It's on GitHub. You can go to GitHub and look at their entire code base. It's all there, open source. Pharo GPL, but it's all there. So that was their answer. It's like, hey, here's some tools. Let's push it out there. I was a little bit cheeky, perhaps. I tend not to be too cheeky on Twitter, but this is during the conference, somebody was talking about Donald Rumsfeld's famous unknown unknowns, right? The known knowns, known unknowns. Well, that's a contingency table. There's known knowns and known unknown. Nobody talks about the unknown knowns, right? The things everybody knows about, but nobody's talking about. Right, and that's what it felt like at Strata a little bit, is all the unknown knowns. There's a lot of ways to do this besides kind of the way that's being produced. All right, so why does it matter, and why Python? At the end of the day, I have the same feeling, right? I don't want to wake up. In fact, it was just last year, I saw kind of the rise of MongoDB. A lot of people using MongoDB, and to write a stored procedure in MongoDB, you whip out your JavaScript and start plugging away in JavaScript. And I thought, I don't want to wake up 5 years from now and have to write JavaScript, right, in order to do my data analysis. It's like there's so much we've done to allow Python to be used simply for data analysis, and yet in big data, in moving code to data, we're retrogressing. We're now using sort of less and inferior languages to do it. So that's what are the strengths of Python? Why have we seen Python actually be pushed and be used? Robert Kern, who many of you know from the scientific community, has a great quote. When you ask him, and if you know Robert Kern, you've met him, he doesn't mince words. He doesn't sort of talk to hear himself talk. In fact, if you ask him a question, he'll often just pause and stare at you for about 30 seconds while you're fidgeting. I know I said something dumb. And he'll come out with a reasoned response. When you ask him, why do you use Python? He says, it stays out of my way, right? I'm not fighting with the syntax in order to do what I want to do. And I think that's beautiful. It's exactly right. The syntax stays out of your way. The fact that Guido, who's here with us actually, that wrote Python as a teaching language, I think is really significant. It was meant so people can understand it. And that's actually been the reason why it's flooded the scientific computing use, where you have domain experts who have all this stuff in their head. They don't want to be also thinking about pointer arithmetic and hash tables and what's the difference between a B tree and a KD tree and how do I unravel. They just want to write code that translates what's in their head to the computer as quickly and efficiently as possible. And then Python has, partly because of that syntax, it has unparalleled integration across technology. Python's been the ultimate glue language, right? That's why scientists have used it for now 15, 17 years, because it allows them to reuse their code. They don't have to be siloed. If I want to use Python, now I've got to go over here. Until the big data movement, I guess that's kind of what I'm noticing. And then it's got this kitchen sink included ecosystem of outstanding tools. I mean, Python distribution comes with batteries included, but if you look beyond just the standard library, there's an enormous number. It's just, I mean, you've all had that fun with Google going, hey, I want to do this, search for it in Python, and what do you know, there's probably 3 or 4 packages that at least are in that direction of doing something like that. And then a very vibrant community, as illustrated by this conference. I mean, the fact that you can basically tweet that we're going to have a Python data hack night and 100 people respond within 2 days. There's a bunch of users out there, a bunch of people who care, a bunch of people who are trying to make things better. All right, so I know some of you are unfamiliar. Let's actually raise of hands. Who has not used NumPy? Okay, sorry, maybe that was the wrong question. Make you kind of, yeah, sorry, I haven't. Who uses NumPy every day? Raise your hand there. Okay. Okay, so there's a few folks who have used it, probably heard of it. Probably didn't realize it's on your Mac laptop. If you just type Python, you can import NumPy, so it's distributed with OS X. I'll give a little overview of what NumPy is and a little bit of history. I mean, I've given talks in the past that have talked about the history of NumPy and SciPy. This is just very brief. Actually, Jim Fulton, I credit with the introduction of the matrix object into Python. In 1994, he had a little post to a matrix sig list and kind of said, here's my matrix object for Python. And it was Python-only syntax, and he wrote this matrix object. And it was pretty good. And Jim Huguenin looked at that. He was a grad student at MIT at the time and said, oh, cool. I mean, showing the power of code sharing and code reuse. These two had never met. They don't know each other, but they knew each other because of this community. And Jim said, I like that. And so he took time off of his research schedule or whatever schedule he was on and wrote numeric. That's right. And wrote numeric and did some amazing things. I mean, he introduced the concept of ufuncs. And in doing so, as we'll see later, he learned from other languages before him. So wrote in numeric, that came out in 1995. I showed up because numeric existed. I started using Python because numeric existed. If it hadn't existed, I'd probably still be, I don't know, I'd probably be in grad school still. I don't know. My wife might be happier. I might still be in Rochester, Minnesota as a research associate at Mayo. As I started to get sucked into the community, writing a lot of code, realizing, okay, I was excited about SciPy. I was excited about reusing Python instead of MATLAB, but realizing there needed to be packages still, and going out and there's a bunch of things that do the job, but how do we pull this in and wrap it into Python? In the process of doing that, there's people who say, well, numeric needs some work. There's some things I'd like to see in it that aren't there. And NumArray started to be emerged as a solution in 2001. That tended to split the community, which I wasn't happy about. I like people to work together. I mean, at the end of the day, I don't like seeing. I think it's useful to have different approaches, but if you can share, let's share, right? That's kind of the perspective. So in 2005, NumPy was released, and fortunately, it's kind of become the array package that people use for Python. Now, it's actually an ancestor. You've got to give a lot of credit to Ken Iverson in 1964. Ken was, I think, one of the first people who recognized the power of writing array-oriented syntax. Right? Rather than forcing people to write for loops and take a programmer who's thinking about just matrix operations, it goes beyond matrix operations, but imagine that. Rather than thinking, I want to do A times B, having to go, okay, now I want 2 for loops here and 1 cross for loop here. Once you do that, and then that's what you hand to the compiler, you actually lose information. The computer can do a much better job with the high-level information that the domain expert, the person who knows what they're doing, can provide. Ken recognized that, wrote a language called APL, which has many descendants, actually. MATLAB, NumPy, all descend from APL. The problem with APL is the syntax. It was a really nice idea to have vector expressions, but the syntax was really difficult. I like to show the syntax with this Conway's Game of Life. I hope, who's seen Conway's Game of Life? Raise your hand. I hope I don't have to explain it too much. The dead cell comes alive based on the neighbors around it. interesting patterns emerge. It's one of these, first simple rules lead to complex emergent ideas. So in one line, you can write Conway's Game of Life in APL, right? So interesting hieroglyphics. Yeah. You need a Rosetta Stone to figure out what in the heck that is. It's worse than Perl, right? I mean, I was just had dinner last night with somebody who said he wrote Perl, 100,000 lines of Perl, went back to it a year later, had no idea what it was doing. Worse, took his graduate student and had no idea what they'd written the previous day. I mean, again, syntax matters. And there are really nice ideas there, but it's really hard to come across. In NumPy, it's a little more verbose, but it's still pretty compact. I mean, there's some initialization code that I'm showing there, but you can implement Conway's Game of Life basically by iterating on this update step, which is 2 lines, using array-oriented primitives, right? So you don't explicitly describe the for loops, you just describe what you want to do. And that's the idea of array-oriented programming. The NumPy array really is a header describing a bunch of homogeneous data. Right? So that homogeneous data is interpreted as an n-dimensional array based on shape information in the header. And it's also that every NumPy array starts with a contiguous chunk, but a particular NumPy array may not have to be a contiguous chunk if it's been sliced, if you've sliced out a version from another one. So some parent of a NumPy array is a contiguous chunk, but the one you've got a hold of might not be. So there's something called strides information that provides that. The other thing the NumPy array provides is this data type object. The data type object allows you it just describes what's in that memory region for every element. And if you're used to MATLAB or IDL, you're familiar with floats or ints or complex numbers as your data type. It starts to get a little interesting for general data analysis when you see the data type can be anything. Data type can be an arbitrary structured array, it can be an arbitrary nested array, it can be a string and a float and then another array inside of it. And it gets your taste buds whetted for this ability to do all kinds of data analysis. Now it doesn't get you all the way there, but it gets you started to think about, wow, I could really use this for some incredible things. But the essentials of NumPy are that is a data structure, that NumPy ND array object that allows you to do the slicing. Basically, I can map a description over data and then access it with slicing and pull out columns, pull out rows, pull out fields, and just do all kinds of manipulations at a high level without thinking about writing for loops and interacting with individual pieces of memory. The other piece of NumPy that's its essential core is the fast math. It's got sums, reductions, array math. You can just type an array plus an array and get a result. I just want to show briefly for perhaps those who have not done this, kind of what that might look like. Right, and you can feel free to do this with your distribution as well. So the PyLab just brings a lot of things in the namespace. Something like linspace, which lets me go like this. And then I can basically compute a sync function. If I plot that, you see figure 1. I haven't gone nearly far enough to be interesting. All right, there we go, a little more interesting. All right, and then I can do things like I'm going to create a plot x where y is greater than 0 and y where y is greater than 0 with a red dot. Right? It lets me do this sort of thing where I can do array expressions to grab out particular elements, plot those particular elements. Y greater than 0, if you kind of unroll what that's doing, it creates a mask array of booleans. And then you index with that mask array to extract just those elements out. You can see how the syntax supports it. Actually, one of the reasons numeric was successful, I think, is because Guido did a lot of things to support, in the syntax, things that were needed by numeric. you look specifically at complex numbers. Complex numbers were added at an early time, and that was a hugely important thing for it to be useful for scientific computing, to have language support for complex numbers. Multidimensional slice syntax. For a long time, it was this extension module that existed. It was the only thing that didn't use multidimensional slice syntax, right? And what that really amounted to was just simply allowing not having to put parentheses around tuples, just in the set item or the get item, allowing a tuple to be constructed just with commas. All right, so that's very briefest overview. If you haven't seen it before, kind of what, I guess we can, the slicing, you can pull out a slice. I can go from 10 to 20 and just pull a piece of that out. I can step through every second. I can just pull out pieces of this array very, very quickly and then do operations on this array. Multiply by 2, add 10 in place to just those elements. And that's the sort of thing you can do at a high level with NumPy. So a NumPy array has different methods. It has a shape, item size. It has what's called this D-type. This D-type turns out to be a very important concept for NumPy. The D-type is the kind of the element. Here, this syntax, it shows that it's a little Indian floating point, 8-byte floating point. D-types can actually be big or little Indian. That was a feature that allows D-types to just memory map over data, where that data might be stored in big Indian or little Indian format. And so it's seamless. You can just map your description on top of the data, and then when the processor does the work, it does the byte swapping behind the scenes for you. There's actually some interesting ideas about how that where we could go with that a little later. The memory model, I think I'll skip for now. Array slicing, we talked a little bit about, but the big deal about NumPy that is, most people love it. A few people early on say, oh, this is really dangerous, is the idea that when you take a slice, you get a view back. The memory model allows that to happen. So you just have a new description of the same data, the same memory. It now is described slightly differently. You just have to be careful about that. It's now a mutable object, so if you change the view, you'll change the underlying memory. The power of that is that it allows you to do things in many other languages. Memory explodes really, really quickly with the simplest operations, and that doesn't happen with NumPy. So that's been a real feature. And another feature of NumPy is just the enormous number of types that it supports. It supports all of the C types, basically. Signed and unsigned bytes, floating point, complex numbers, and then some string types, character, Unicode, and this thing called a void type, which is where really structured data types show up. I can make a data type that is a combination of an integer, a float, and a string, say. Now, every element of the NumPy array is that record. And I can have, then a five-dimensional array of those records. It's pretty straightforward to create. I mean, there's a lot of, there's things that can be improved in how you spell this, but it's pretty simple and pretty straightforward to use. And then when you get out a field, you use indexing notation as well. There is a rec array subclass of the ND array that allows you to use attribute access to get the fields, which is quite popular. And there's some talk and there's been talk for a while of trying to figure out how to do that by default, allow attribute access to the arrays through probably through some intermediate attribute on the array themselves. So that's the array object. The ufuncs are these universal functions that essentially implement the fast UMath. This was one of the key innovations that Jim provided, was this object that will store, it's basically a generic dispatch mechanism, generic function mechanism, where you have an underlying loop for every data type that loops over n elements. And then you have a dispatch mechanism on top that takes whatever calculation you're doing and says, well, okay, which of these underlying loops do I call based on the data types I have? Right? So there's some coercion involved. It gets a little bit messy because you're talking about, okay, floats and unsigned ints, and what's the coercion table, and how do you compute it, and how do you determine it? And some places are actually determined by the compiler. Some implementations are actually determined by whatever platform you have. But that's essentially ufuncs, and they just hand that off to this low-level loop. And to make a ufunc, it's as simple as writing that low-level loop for whatever you want to do, whether it's a sine or a cosine. Currently, or originally, ufuncs only worked element by element. So essentially that low-level loop got one single element from all the input arrays and did something with it and returned the output. There is something called this generalized ufunc. It's a fairly new feature. It's equivalent to Perl's. Perl has a Perl data language called PIDL, and they have something called threading, they call it, interestingly enough, that can take more generic kernels that can actually operate on a whole dimension of the array instead of element by element. And a great contribution by added this to NumPy, although still only for contiguous arrays. It needs to be allowed to support for general arrays. Broadcasting is something that is one of the powers of NumPy arrays. You saw me add and multiply. I took an array and I multiplied by a scalar. And that, what was that supposed to do? Well, it broadcasted the scalar to a full array and then did the operation element by element. Broadcasting can be even a little more depth. If you don't know what it is, I'm not going to teach you in about 2 seconds. If you do know what it is, you don't need me to. So just know that it's something that's important about the way shapes get converted. There's a bunch of available ufuncs there. So generalized ufuncs are, we talked about. All right, so that's NumPy in 10 minutes or less. It sort of serves, it's a foundation for a lot of other packages. Another aspect of NumPy that I didn't talk about is the C API. Python has an API in C. NumPy also has a C API. So you can build extension modules to Python that use NumPy from the C level. It's a very actually popular API, and a lot of people use it to do other things down the stack. Important to keep in mind because NumPy is more than just a few Python calls. It's actually got it's C infrastructure, just like Python does. SciPy is where when I started with Python, I was just wanting to see a MATLAB equivalent. That's kind of where my mind was. I wanted to see integration. I wanted to see interpolation, linear algebra, optimization. And I noticed that we can get there by, there's a lot of packages out on the net. There's a netlib.org. I think it's still around, right? There's a bunch of Fortran code that's been used for years, MinPack, ODEPack. So you start pulling that in, putting nice Python wrappers around it. I did it by hand. People kind of came in and said, what are you doing? Let me do this. Let me automate this for you. Yeah, maybe I'm not really a Python. Maybe I'm more of a mathematician than a hacker, right? Because you can always tell a hacker because they'll automate a problem. Right? I'm always just trying to just get the problem solved, even if I don't automate it. But SciPy, fortunately, lots of people have jumped in and helped SciPy grow to where it is today. The core set has stayed pretty constant, although spatial has been added. ODR isn't listed here. It's been added. Cluster, stats has received a lot of attention by Joseph Perktold. The special functions have basically been added to a little bit. But it's this huge collection now of tools for doing all kinds of things. A basic core set of things you might want to do in data analytics, essentially. Simple example. This is what code might look like that's using SciPy. This was an example I gave actually 4 or 5 years ago at a SciPy conference where I took pictures of a bunch of people and then tried to find the eigenimage of everybody, right? So let me do a singular value decomposition on the images and then just look at the first 3 eigenimages, right, of all those people. It's just kind of a cute example of how you might read images, reshape them into a 2D array, call the SVD, on the red, green, and blue channels, insert the first vector back into a new image, and then save out those images. And that's a bunch of SciPy people. That's their eigenimage. They all look like that. There's your amorphous Python hacker. Of course, the first one looks pretty good. Then the second one, the colors, it's not quite the same. Not quite the same averages. Curve fitting is another common example I show. Actually, Microsoft hired Enthought while I was there to port NumPy and SciPy to the .NET platform. Unfortunately, Microsoft changed their directions sort of right when that project started. That's the time Jim Huguenin became a Google employee as well. So it didn't quite get to where I think it could have been. But one of the things it showed is I went and tried to figure out, well, which of the SciPy modules get used? Like what, and how do I figure that out? Well, I went to code.google.com, which is a pretty nice tool, and I searched. There's a way to search kind of all open source code that it's been able to crawl, and I searched for import SciPy, basically, and tried to see, what packages out there use SciPy? And then if they did, which sub-packages did they use? Interesting results. I mean, actually, you can probably predict yourselves what packages were in common use. It's basically optimized linear algebra stats with some special functions. Optimized, so the dominant use case of SciPy was optimized stats linear algebra, right, which makes a lot of sense. Curve fitting, this is you have a function, I have data, here I'm just generating data. It's a simple, I'm taking data and then I'm adding some noise. In practice, you might get data that's noisy you think fits this function. Here I'm generating that data on the fly. So you have this noisy data yn, you have the independent axis x, and then the function you're trying to fit to those data. And curve fit does that for you pretty quickly, gives you out the optimal parameters as well as a covariance estimate on those parameters. So very simple function to use to make for a common use case that people have. All right, so now that I only have 9 minutes left, basically for the past 4.5 years, I've had the great chance at NThought to work with a lot of people in industry who are using Python. And I've seen a lot of people using NumPy as well as SciPy to get a lot of work done. But I've also found that there are things they're not using NumPy for that I think they should be. It's like, they should be using NumPy for that. Why aren't you? And as you dig a little deeper, you realize, okay, yeah, you're right. There's that little low-hanging fruit. It's kind of a little bit of, if NumPy had this, then it would map to your problem better. It would allow you to solve what you're trying to do a little better. And so kind of over that time, I've built up this long list of things I wish NumPy could do and could have. And sort of these that are here. And hopefully be able to talk more about these over the coming months. I'll be putting NumPy enhancement proposals to the mailing list, getting community feedback on a lot of these ideas to try to get and change what's in NumPy, really move NumPy forward, push it forward to where it needs to be, I think, given the kinds of problems we're trying to solve, given the kinds of things people are trying to do, and really just promote using Python to do the analysis instead of JavaScript or Java or some other version of a language. Or if there is a DSL that we use, great, use that DSL, but have it essentially be a lightweight DSL on top of Python. So there's a Python library that essentially undergirds it so that the code reuse can occur. So this is just a couple of, so the ND array, I think we need to have indices, especially for structured arrays. I'd like to see a SQL front end, multi-level hierarchical labels. Some of this stuff actually you'll hear in pandas. I mean, Wes is pioneering a lot of things that I really like to see. My only complaint is I want that stuff in NumPy too. I don't want it just in data frames. Like I would love to see the day where a data frame is a view on top of a NumPy array. We're not there yet. Wes has been doing a tremendous work to actually solve user stories and use cases and make people's lives better. It's wonderful work he's doing. If you haven't checked it out, make sure you see the pandas talk. But a lot of the stuff he's doing, I'd like to see just available on NumPy arrays as well. The global array, the distributed array, there's a lot to think about there. And I think the start of that is actually memory spaces. Instead of having an array just be a single chunk, having an array be at least multiple chunks. And we can talk more about that actually. Standardized distributed persistence. Fancy indexing is a view. Optimizations to there. Streaming arrays. There's some ideas I'll talk about a little later. I also relate to that. I think D types need some improvements. I think there needs to be an enumerated type, categorical data. And thanks to my friend Lev here, actually has a wonderful idea for dynamic enumeration. I hope to see that added soon. An idea called derived fields. And to give you an idea of what I mean by a derived field, I mean the ability to find a D type like this, let's say, kind of a class description where you have different types. And then one field, it doesn't exist. It just is computed on the fly. It's not stored anywhere, but it's just a calculated version of the other fields. And I call that a computed column. I go to derived field as soon as you want to do a insert. Now I want to do the set item. How do you do that? How do I take somebody inserting data? What happens then? Where does the data actually update? So how do we make that possible so that calculation is done, not in Python runtime, but at least expressed with Python syntax, but then converted to something that happens very, very quickly. The date time needs to be finished. A varchar data type, a string data type essentially. So you don't have to know exactly how many you're going to have. And then missing data, I think it's important to really nail the missing data question. And then there's some other ideas there as well. UFUNCs need to be improved. There needs to be generalized UFUNC support more than just contiguous arrays. Specification of UFUNCs in Python. and we'll talk more about that. Move most data type array functions to ufuncs. There's a lot there. If you look at the details of how NumPy is implemented, there's the universal functions, which is this generic function calculation hierarchy, and there's the data type. And the data type doesn't always use that generic function dispatch mechanism. It has also some function pointers hanging off of it. And I'd really like to have a framework where that is minimized. Most of it just goes through this generic function dispatch mechanism. So once you add these generalized ufuncs, a lot of that can happen. And how close are we? Error handling, unification for the dot product, basically. Ufuncs have unified error handling, but some of the other calculations don't. Lazy evaluation and remote computation is something I think a lot about. Ultimately, we all know we got to move code to data. I want that code that's moved to data to be Python. That's, in a nutshell, what I want to see. So how do we make that happen? Right? So that you, as a researcher, can write Python code, yet you know the data is actually distributed all over the place, and you're not going to pull the data to you. You got to push the code to the data. But you don't want to have, okay, that code, I actually have to rewrite that now in JavaScript or some combination of JavaScript plus Java plus R plus something else. How do I just use what you're doing and push it to the code, the data that's sitting there? Multi-core, GPU optimized ufuncs, there's a lot to be done there. And then group by reduction. All right, there's a ton of work to do. I hope to explain an idea I have about how to incorporate LLVM. There's some interesting work I'd like some help with, actually. It allows you to specify Python and then translate to LLVM and then run in machine code and insert that into the NumPy runtime at various places. All right, so there's a lot of work. So the approach that I'm taking, right, because I see this work needs to be done and I'm just really excited to do it. So how am I going to do this? Right, well, so I've started a company with Peter, right, and we're going to be focused on the enterprise, trying to figure out how to get money from the enterprise, basically, from folks that are using big data, pull it and channel it to the NumPy development, right? But at the same time, we've also started a foundation. The foundation is called NumFocus, and I wanted to talk about that just a little bit. So NumFocus, you can go to the website now, www.numfocus.org. It's just nascent. It's just getting started. The person that is actually full-time administrator for the foundation has been working night and day to get this website up this week. She's been doing a good job. So the mission of the NumFocus Foundation really is to undergird and make sure that all the software that people are using for scientific data analysis stays open source, is supported. Try to figure out how to get money from people that are using the tools, but not necessarily they just want to support a foundation. Actually, it was interesting to hear Doug Cutting talk about the Apache Software Foundation. And I see in that a model, kind of what we're trying to do. We're trying to, for Python, for scientific computing, create a foundation that people can use and get behind that'll channel money towards the projects themselves. So currently, we have sponsored projects, and the sponsored projects that we have now are basically because people have stepped up and said they would be willing to accept the money and do something with it, do something productive with it. And so right now, currently sponsored projects are NumPy, SciPy, Matplotlib, IPython. Basically, joining me on the board of NumFocus are Jared Millman, I think he's here, right? John Hunter's here, author of Matplotlib. Fernando Perez, author of IPython and Python evangelist extraordinaire. I've seen him give a talk to the SIAM conference for a day straight. I mean, he gave 15 people's talks. It was, if I'd known he would do that, I would just stayed home and said, hey, give my talk too. But he's enormous energy and enormous ability to articulate the Python position, and it's great to have him. And then Perry Greenfield of the Space Telescope Science Institute. Current board of directors, we're right now just organizing, trying to figure out, okay, how are we going to move forward? The idea of members is coming soon, and right now we can take sponsors and donors, and we're trying to get money out to people this summer, right? So there's equipment grants, boot camp in a box, figure out how to teach people Python quickly and fund those boot camps, and then figure out how to even possibly buying out faculty time from folks or buying out graduate student time, so people can spend their time making the tools better and stronger. So that's the mission of NumFocus. If you're interested in getting involved, so far it's all volunteers that are sharing their time doing this, except the full-time administrator we have. Anthony Skopats is acting as the treasurer. There is still a need, I think, for other people who can come in and volunteer their time to help in many ways. So If you're interested, actually me or Jared here, you're going to be here all weekend. Jared's a great one. He's in the Bay Area. He'll be in grad school soon, right? Which is the first part of grad school is great because there's no pressure. So. No, you have all this time, right? Paul's here. All this time. That's actually not true. It's actually that after your first batch of classes where you've got that, you finish your classwork, then you've got this sort of, okay, I just got a thesis to finish, but that's not forever. I don't have to defend that forever. So I got 2 years to do whatever I want. Yeah. Look where that goes. The goal is to sponsor sprints and conferences and just do whatever we can to improve the state of the code base. And there's some other ideas that Fernando Perez is talking about, perhaps putting an Uber package together. There are a lot of things I think we can talk about today and into the next couple of days about how to make that better. So in the end, to conclude, why aren't we doing better? It's the data, right? It's the data. Hadoop's dirty secret, I think, is that most of the uses are just the Hadoop file system. It's just an easy way for people to stick their data out on a bunch of machines. Now, actually using the Hadoop runtime, MapReduce runtime, there's a lot of proof of concepts out there, but it's not used that often in production. So what are the distributed data storage solutions for Python? How do you create and just get data, make it available to everybody? But as you're moving code to data, let's make that Python. Right? If the distributed data solution is requiring you to write code in some other language or some other stack, it's not good enough. It's not good enough for me. I'm not excited about it. I'm going to try to figure out some way to replace it if that's the case. So, that's the gloves are off. That's what I'm trying to do. I want to make Python universal in this code reuse. Just a slide I put together, kind of start to explain some of the ways I think about this problem of the software stack. When you talk about moving code to data, you're really getting at the heart of the software stack. Because what is the code you're sending to the data? Well, it's some combination of Python, a C runtime. If you're using JavaScript, then what's its runtime, and then translated through these other 15 layers. What is that code, and how does it run? I'm starting to really like this model, right, of how you think about the software stack, right? You have plateaus of code reuse, right? C for a long time has been this place where people can come together, share libraries. I'd actually like to see that low level kind of, there's this low level virtual machine called LLVM. If you don't know about it, come talk to me, we can talk about it. I'd like to see high bandwidth connections between Python and a low level virtual machine that allows Python to be a plateau of code reuse at the high level. And then have little DSLs, domain-specific languages, R, MATLAB. I'd love to see all those just be domain-specific languages, where the library support is all Python, and then in the very same way that C and C++ are just DSLs for LLVM. Now that CLang exists. That's tongue-in-cheek. It's a little, I'm not entirely serious, but nonetheless, you see a lot of people get on this bandwagon. Apple, currently, their compiler stack is using LLVM as a low-level assembly. That's in their compiler chain. You have Dragon Egg that allows GCC, any GCC language to essentially emit LLVM instead of the, and then allow that code gen to happen there. You see NVIDIA using their backend. They have LLVM, and then they emit GPU code from there. It's a nice place where at the hardware level and the low level, there's some cooperation happening so that significant code reuse can take place. That's all I've got. I appreciate everybody here. I'm excited for the talks, excited for what you're going to present, and looking forward to talking to anybody about anything you've got. All right, thanks.